Momentum, conservation of momentum. Conservation of momentum, energy, momentum is conserved, energy is not. Number 67, a 5 times 10 to the 5th kilogram railroad car collides with a stationary railroad car of equal mass. After the collision, the two cars lock together and move off. What kind of collision is that? Inelastic. Very good. So we're going to draw the before and the after. So here's the after. Draw them stuck together. And then the before. Why did I draw the after first? Well, because the picture was in reverse. That's why. Okay, I'm sorry that messed everybody up. But this is before, that's after. Okay, so that's after. Now they lock together. So what do you do with the masses if they lock together? You add them up. Good. Okay, there's car 1, there's car 2, there's car 1, there's car 2. So you add them up. So that would be technically 2 times 5.0 times 10 to the 5th kilograms. I just multiplied them times 2 since that's what you're doing if they have the same mass anyway. Right, James? My man James is savvy. He knows what's going on. Okay, and after the collision, they lock together and move off. Before over here, again, they have the mass of 5.0 times 10 to the 5th. This one is at rest. So velocity initial is 0. This one has the same mass, 5.0 times 10 to the 5th kilograms. And what was the initial? Before A here, we're on A. Before the collision, the first railroad car was moving at 8 meters per second. Okay, we'll make this one 8 just because it said first. Whatever, okay? This one's 0, this one's 8. Doesn't matter. Point is they lock together. Right? Okay. So we're interested in finding the final velocity. So there you go. What is this, guys? What's this mass? 2 times 5 times 10 to the 5th. What's that mass? Sure, I'll put the formula for the inelastic. So you're going to add the two masses, okay? And that's equal to the mass of 1 times the initial velocity of 1 plus mass of 2, initial velocity of 2. 1 million. So 10 times 10 to the 5th is 1 times 10 to the 6th. Good, Logan. So 1 times 10 to the 6th kilograms, okay, times final velocity is 5 point, well, this is just 0 then. If this one's standing at 0, I just labeled it 0. Okay. Gosh, that's ugly. I apologize. Trying to be more professional here. 0 meters per second, that means this whole thing was 0. So that's 0. Plus 5.0 times 10 to the 5th kilograms times 8 meters per second. So guys, multiply these two, divide by 1,000,000. Multiply those two numbers, divide by 1,000,000. Use parentheses. Let's see, 35. What do you get? Decimal something? What do you guys get? 4? Everybody concur? 4? You guys with the TI-83, Chris Perham, is it 4? 4 meters per second it is. Which would make sense because if this is 8 with half the mass and all of a sudden, Ryan, we double the mass, then we half the velocity. Okay? That was simple. But number B, what was number B here? What was the total momentum of the two cars after the collision? So we're just interested in this part right here. We're only interested in the P after. What was the total momentum of the two cars after the collision? That's for part B. So just for part B, we're only interested in P equals mass times velocity. Now, the velocity was 4. That was 1,000,000. So indigo, it was what? 1,000,000, 1 times 10 to the 6th kilograms times 4 meters per second. I'm assuming that's 4 million. Yep. Yeah. 4 times 10 to the 6th kilogram meter per second. Now for number C, guys. Were the kinetic energies of the two cars before and after the collision? What were the kinetic energies? Uh-oh. How do you do kinetic energy? What is the equation for those? 1/2 mass times velocity squared. So now I'm going to erase this bottom part. Okay. I'm going to erase the bottom part. And we are going to do the kinetic energies for the cars before and after. If it's not moving automatically, Logan, you know car number 1 is not moving, so the kinetic energy for that one is what? It's 0. Okay, 0. So here we go. Now we have to find the kinetic energies for each one of these guys. Well, the kinetic energy of this guy is 0. The kinetic energy of this guy, 1/2 mv squared. You guys solve that. The kinetic energy for these guys is 1/2, and then you have to double the mass. So double the masses, v squared. What's the kinetic energy for these guys? Okay, 1/2, 5 times 10 to the 5th times 8. What is that? 3.5 times 10 to the 6? Multiply 500,000 times 8. What do you get? 8 squared. Boy, was I wrong? My bad. So that's a big old number. James, what do you have, sir? 1.6 times 10 to the 7th joules. 1.6 times 10 to the 7th joules. Now, is our kinetic energy over here supposed to be the same as this side? No, it is not. Because when you smash train cars together, they make a tremendous noise. There's a heat exchange. There's deformed metal. So now what? You've got 1,000,000 kilograms, okay, times 1/2, times 4 meters per second. The velocity final there was 4 meters per second. 1/2 times 1 times 10 to the 6 kilograms times 4 meters per second, and square that. Okay? What'd you get, guys? 8 times 10 to the 6th joules. Well, it would appear that the kinetic energies are not equal. Somebody tell me why the kinetic energies are not equal. You lost it. You lost it to thermal, to sound, to deforming of the metal. Quank. Okay? Whatever noise. Psh, humongous bang. Okay? Yeah. So was momentum the same on both sides? Yes, it was. Is kinetic energy the same on both sides? No, it is not. So count for the change in kinetic energy. So we said it was sound. We said it was heat. We said it was sparks. We said it was deforming of metal. Was it friction in the wheels? Did we lose it to friction too? Frictions in the wheels. Well, that would be part of it, the collision heat, and then you also have frictions in the wheels too. Yeah? Who has questions about that? Who still can't get their head around that energy goes places? It's not all conserved in the same place. It's lost to the environment. Still don't get it? Momentum is always conserved. Energy is not. Period.